We're going to talk about inverse functions. Now this is actually for calculus, but I'm going to review some algebra. So inverse functions. Inverse functions undo what has been done. So notation, first of all. Notation, f of x is a function, and f inverse looks like this. F inverse looks like that. Something else about inverse functions is f of x and f inverse of x are what are called mirror images over y equals x. So to give you an example, let's say I have this. I'm going to take the exponential function, e to the x. So there's e to the x, y equals e to the x. Its inverse is the logarithmic function, ln x. ln x is f inverse of x. So that's f of x. Now my artwork is horrendous, but if I drew the line y equals x in here, and if I had a good graph, then this line would land on this one, and this one would land on this one if I reflected them over. So that is a reflective property. Some other things about inverses. Notice that when the exponential increases, so does the inverse. So if f increases, so does f inverse. If f decreases, so does f inverse. Also, if f is continuous, then so is f inverse. So you might notice that we can do a whole lot of things with inverses if we know the original function or if we know the inverse. Now, something that you probably learned in college algebra was that in order to have an inverse, a function has to pass the horizontal line test. Otherwise, an inverse will not be a function. For instance, if I've got the function y equals x squared, which is a parabola, if I run a horizontal line through that, it's going to hit more than one point. That does not pass the horizontal line test. Now, if you look at the reflection of that, it's not a function. So it has got to pass the horizontal line test. Now in calculus, we've got a little bit nicer way to talk about that. And that is, in order for something to pass a horizontal line test, the function must be monotonic. Now what does that mean? It means that it's always increasing or always decreasing. And we can use derivatives to find that. So that's something you probably did not do in college algebra, I'm guessing. But if something is always increasing or always decreasing, then it's not going to turn around and come back, which is going to keep it passing the horizontal line test. Now let's show how we verify inverses. So let's verify a function's inverse. So let's say we've got f of x is equal to 4 minus x to the third, And my claim is that f inverse of x is the cube root of 4 minus x. Now, how do I verify that? Well, here's how I do that. I can take f of f inverse of x, which is f of, and I'm going to put this, 4 minus x, that's f inverse. And it doesn't matter what order you do this in when you're verifying. But the f function takes whatever is in the x slot and puts it in the x slot here. So this is going to be 4 minus this stuff, this f inverse function cubed. So what I get is I get 4 minus cube root cubed, that just drops out. So we've got 4 minus x. And we end up with 4 minus 4 plus x. That drops out. We get x. Now, if you get x, then you have verified it. So that is verified. It's related to the line y equals x. All right? So that is how you verify, by taking the composition. And you've probably done composition quite a bit in algebra. Let's try another one. This one is g of x, and it is 1 over 1 plus x. You can leave that alone. You can try to work on the whole thing, whatever. That one is a function that we could look at graphically, which I think would be a good idea here. So let's take 1 divided by 1 plus x. 1 plus x. And I'm going to do zoom standard so we can kind of see that. Here's the function. Now, that is always decreasing. It's got a horizontal asymptote, vertical asymptote, then it picks up vertical asymptote and horizontal asymptote. Horizontal asymptote's at 0, vertical is at -1, but it's always decreasing. Now, sometimes people like to do inverses, like only half of the graph, and what I mean by half is cut it off at the vertical asymptote. So sometimes that is like given in a book or whatever. We could do the whole thing, because this is a one-to-one function. It passes the horizontal line test. That's what one-to-one can be associated with as well, but it's always decreasing. It is not defined right here, but that when we reflect that over the line y equals x, it's going to become a horizontal asymptote. All right, so let's take a look at this. My claim is that the inverse function is equal to 1 minus x over x. Now let's see if that is the case. First of all, let's just look at the graph. I think that would be kind of interesting. So let's take this graph. It is 1 minus x divided by x. And I am going to do zoom square so that the graph will look as accurate as possible. So here's the original, it's in blue, and here is the inverse. Now, if I draw the line y equals x, I think you'd be able to see that this blue line reflects over to the red line. Something you might notice, you probably noticed before, is if you're using a TI 83 or 84, it kind of dies on the vine, so to speak. It does not do the vertical asymptote all the way. That's a technology issue. That is not a real life issue. That line continues forever in a vertical fashion. So we really do have vertical inverses. Okay, so, or vertical tangents, not tangents, vertical asymptotes. There we go, vertical asymptotes. All right, now let's validate this. So I'm going to do this one the opposite direction because it doesn't matter. So I'm going to take G inverse of G of X. So this is G inverse of 1 over 1 plus x, that's g of x, and g inverse takes 1 minus whatever's in the parentheses over what's in the parentheses. So 1 minus 1 over 1 plus x over what's in the parentheses, 1 over 1 plus x. Now that's kind of a hassle, but it's okay. Let's multiply by 1 plus x over 1 plus x. What do we get? Well, we get this here, so we've got 1 plus x minus, and then these cancel, so minus 1. This cancels here, so we've got 1, so the result is x, which tells us that it is verified. So there we go. Now, that's algebra stuff. So we can use some of the algebra stuff. There's some more algebra, and that is, how do you find an inverse? So finding inverses. You may have learned this differently than I'm going to show you, and it doesn't matter if you have a little different style, as long as the basic rules are followed, that's fine. My order is mine. So here's what I like to do to find an inverse. Given f of x is equal to the cube root of x minus 1. I'm going to find f inverse. So step 1, I write y equals the cube root of x minus 1. Step 2, I swap x and y. So every place there's an x, I put a y. Every place there's a y, I put an x. So now I've got x equals the cube root of y minus 1. Then step 3 is the most challenging because it's got some algebra, but I've got to solve for y. This is the new y. So I've got to cube both sides. This one's not too hard. Cube this side, I get y minus 1. Add 1 to both sides, I get x cubed plus 1 equals y. And then number 4 step is to call the new y f inverse of x. So I've got, that is x cubed plus 1. And then step 5 is to validate that it really is the inverse. So f of f inverse, if I do it in that order, of x, I get this one first. So f of x cubed plus 1. F takes the cube root of this thing, subtract 1. Well, plus 1 minus 1, cube root, that's equal to x, so it's verified or validated. So those are some things from algebra that you might want to do to work on inverses. Now, let's do a little bit of work with calculus, because we have got to use this for calculus. There is a theorem in calculus that says this, that if g prime is needing to be found, okay, so g prime of x is equal to 1 over f prime of g of x if g is the inverse of f. Okay, now that's kind of wild looking. What it's basically saying is that you've got to do composition, and you really don't have to find the inverse of g, or you don't really have to find the derivative, let me tell you that, of the inverse function. So let's look at an example, see how that works. Now you can always do derivatives of inverses and such just by taking derivatives. That is not a problem, but this could help you possibly. So I'm going to do this. I'm going to take f of x is equal to 1/3 x minus 8. So there's f of x. Now g has got to be its inverse. So if g is its inverse, then g of x, let me find the inverse again, do the algebra. So y equals 1/3 x minus 8. So solving or flopping those back and forth, x equals 1/3 y minus 8. That gives me x plus 8. So x plus 8 equals 1/3 y. Multiply both sides by 3. I've got 3x plus 24 is equal to y is equal to f inverse of x, which we're going to call g of x, just to fit this. All right? Now, what is g prime of x? So the question would be, what is g prime of x? Now, there's some notation I want to show you. What is g of x? G of x is f inverse. So it's equal to f inverse of x prime. That's pretty wild looking, okay? You could also say this. You could call it d dx of f inverse of x. So that's pretty wild looking because we've got inverse and derivative in the same thing. Now, let's put some other work here. This says that g prime of x is equal to 1 over f prime of g of x. So what's f prime of x? G prime, so according to the theorem, g prime of x is equal to 1 over f prime of g of x. And f prime, if you look here, f prime is 1/3. So this is 1 over, and 1/3 doesn't have any x's. So it's just 1 over 1/3, which is 3. Okay? Well, what is g prime of x? 3. Now that may not prove it to you because they're just constants, but that's kind of a cool result. Okay? Let's try something else. See what happens with another example. Let's take f of x is equal to e to the x. Now, the derivative of f is e to the x. It's itself. Fine. What is the inverse of e to the x? Well, g of x is the natural log of x, and I'm not even going to bother finding it. Okay? So, now, the question would be, what is g prime of x? What's the derivative of log x? Well, you might remember that, but let's show it with this. So g prime of x, according to this, is 1 over f prime of g of x, which is 1 over f prime of x is e to the x, so it's e to the g of x, which is 1 over e to the ln x, which is 1 over x. So that might be of some help to you. So that's the calculus part that relates here. It's a relationship between derivatives, and there's some composition involved, so you may or may not like using it. You could literally find the derivative of g of x, but you'd have to find the inverse. So if you don't know the inverse, then that's something that you're going to have to work on. Now, I've got a couple more examples that are more algebraic. Okay, so a couple of examples using notation, just to make sure that you have the notation kind of figure it out. Let's use our f of x that I had a few minutes ago. It is 1/3 x minus 8. And then I'm going to have another function. I'm going to call it h. And it is x to the 5th. All right. So let's look at a few kind of strange looking problems like this. Let's take f inverse of h inverse of 32. That's an h, okay? Well, I don't supposedly have those. Now, I do have f inverse because I found it, I think, up here. But I don't necessarily have this one, although it would be pretty easy to find. All right, but let's take a look at that. First thing we do algebraically is that one. So what is h inverse of 32? Well, that is the same thing as saying the answer to the h function is 32. So it means that 32 equals x to the 5th. Now you might know that one. I chose something that's got a nice answer, so I know that x is 2. Okay, so what is h inverse of 32? Well, it asks you actually for x. H inverse asks for x. So h of x is x to the 5th, so h inverse of h of x is h inverse of x to the 5th is x. By definition, so the answer to this piece is 2. So this is going to translate into f inverse of 2, because this part was equal to 2. So f inverse of 2. Well, that means that the answer to f is 2. So 2 equals 1/3 x minus 8. We've got to solve for x again. Inverse is always answer with x. So add 8 to both sides, you get 10. And so x equals 30. Multiply both sides by 3. So the answer to this problem is 30. Now that's a little bit of notation and some work there. Be careful with what is asked for first. Algebra rules always hold. So there are some examples of inverses.